So actually, I've eventually removed the enterprise Django from the title, but I'm still wearing a shirt because, transaction, it's serious business. I know I'm the last one this morning. We've had a bunch of fantastic speakers, and I hope you'll pardon my French. So I would like to start with a pro-conference tip. If you would ever like to submit a talk, don't submit a talk on a subject you aren't familiar with. Because like 3 months ago, I was thinking, oh, I should submit a talk to DjangoCon. What could I talk about? Well, transaction, I'm not actually sure how these work. I need to investigate that. And I submitted the talk. And I started writing the first version, and I realized that I had absolutely no idea how everything fit together. And I started researching. I downloaded the SQL standard. It's 1,500 pages of reference with not a single explanation of how everything is supposed to fit together. And I read the docs of PostgreSQL, and I read the source of SQLi3, and well, it was a mess. And eventually, I decided I had to rewrite transaction management. So I did that, and I've wrote version 2 of the talk that I'm about to present to you. So the talk is substantially longer than I initially envisioned. It fits in about 1 hour, but since I don't want 1 hour, I will have to speak roughly twice as fast. I hope you don't mind. Okay, anyway, let's go. 2 years ago, Christophe wrote this in a presentation about ORMs. He wrote transaction management tools are often made to seem like a black art. And when I look at Django 1.5 and earlier, I have to admit that he was completely right. Today, I hope to make this slightly less true for Django, at least 1.6 and later. So let's dive in. And I would like to thank Christopher very warmly first, because lots of my work is inspired from his blog and his writing and his talks. So much of the credit goes to him, actually. Anyway, today, we're going to walk up the stack. We're going to start from the database layer, and I'm going to focus on the real open source databases supported by Django, which are the databases not owned by Oracle, namely PostgreSQL and SQLite. They have correct documentation. This also helps. Then we'll move up to the interface layer, which is the Python library we use to access them, namely lifecycle PG2 and SQLite3. And then we'll arrive at our favorite layer, the Django web framework. Is it clear for everyone? So let's start with the SQL standard. SQL more or less begins at SQL 92, which is only a few hundred pages. It's not in the thousands range. And SQL 92 defines an SQL transaction as a sequence of execution of SQL statements that is atomic with respect to recovery. And here the key word is atomic. It means that everything, when you run an SQL transaction, all the statements that you're going to run in the transaction are going to be executed, or none of them are going to be executed. And I've shown, I've extracted graphs from the documentation of SQLite that show how SQLite does this. And it's fairly complicated because it involves writing a rollback journal that contains all the information required to come back to the beginning of the transaction if something falls apart midway. The worst case being you have a power loss or you disconnect your disk or whatever, and then you will end with some data corruption, and SQLite is able to recover from that. This is the schema of how SQLite recovers. Basically, it knows that it has some broken data, and it restores it from the journal, and once it has finished restoring the data, it accepts to move on with more queries. So now let's show a quick example in pure SQL. Well, this is a simulation of returning a car after a rental. That's the business I'm in. So the car becomes available again, and we update the rental to set the end date at now. And we commit the transaction. And you may have noticed that it does not include a begin statement, because begin is not required. In SQL, basically, as soon as you run a statement, you enter a transaction. You don't need to write begin. Basically, running SQL outside of a transaction isn't even a concept that exists. So all you need to do is commit at the end. And this is a transaction. So to sum up the life cycle of a transaction begins with a transaction initiating statement. Virtually every statement you know is transaction initiating. So a transaction begins with a statement, and it ends in one of three ways. Either you run commit, or you run a rollback. That's an explicit rollback if for some reason you decide you don't want to save the changes, or an implicit rollback. And the implicit rollback is what the database does when something goes wrong, and for some reason it can process your commit. So typically this happens if another transaction has written something in the meantime and that conflicts with what you're trying to save, and the database can't make it work, and that's called a serialization failure because the database cannot serialize the two transactions one after the other. Well, specifically regarding this problem of serialization, there's a bunch of isolation levels that describe how the database, well, what the database accepts to do in order to serialize transaction. That helps when you have concurrency. So basically, the only one that's easy to understand is serializable. It means that the end result of a sequence of transactions is exactly the same as if you had been running the transaction one after the other in some order. The others are very complicated, and you can look it up on Wikipedia or wherever if you're interested. Summary of SQL 92. It's fairly basic. You have two statements, commit and a rollback. And well, you have two other statements that are set transaction and set constraints that set some add-ons, properties, and transaction, and you don't need to care about this for now. So let's move on. 7 years later, we have a new standard, SQL:1999. You may have noticed that the naming scheme isn't exactly consistent, and that's, well, very relevant when it comes to SQL, actually. So the main addition in SQL 99 is save points. Save points only exist with a transaction. Let's imagine you have a transaction here at the top with two save points. If you run save point F3, you add a third save point. So this is a transaction where you run queries in the green areas, and I'm representing stuff that matters for transaction in the orange areas. If you run the release save point S2, this is basically a commit. Save point S2 disappears, and you can no longer roll back to this save point. Any further save point also disappears, but you can still roll back to a previous save point. So typically in an application, you create a save point, do a bunch of things that could fail, and if these things work, you can remove the save point because you no longer need it, and so that's release save point. And of course, if something goes wrong, the main advantage of save points is that you can roll back to a save point, and so you just come back to the stage you were in the transaction. There's another small addition in SQL 99, which is explicit transaction start. There's a new statement called start transaction, which basically does nothing because transactions are automatically started, but it will raise an error if you're already in a transaction, and there's another use that we will actually discuss later on. So, summary on SQL 99, we have save point with a save point ID, release save point, rollback to save point, and start transaction. So that's the end of the part about the SQL standard and statement controlling transaction. There's nothing else in the SQL standard that discusses transaction. The key learning is that SQL statements always run in a transaction. Transactions are opened automatically. And, well, there are add-ons technology. When you read the graphs from the SQL docs, you realize that it's hardly distinguishable from magic. At this point, we can have a brief interlude and discuss an error that some of you may have encountered. Who uses PostgreSQL and has never encountered this? Nobody! And it says current transaction is aborted, comment ignored about end of transaction block. And that's incredibly mean because you have absolutely no clue what PostgreSQL is trying to tell you. It's trying to help, and it fails. So I provided an English translation of this statement, which is a previous statement failed, and that's what caused the transaction to be aborted. And so the application has to perform a rollback. And at this point, you may ask, well, PostgreSQL knows that I have to roll back, so why wouldn't it roll back by itself? And in fact, there's a very good reason for not doing this. Imagine you run a bunch of statements, and then one statement fails. If PostgreSQL rollbacks a statement, you can run more statements afterwards. And then in your transaction, all your statements will have executed except the one that failed. And by definition, that's not atomic. So if PostgreSQL was doing this, it would break the very feature that transactions are trying to achieve. So it's up to your application code to notice that you had an error and to decide what kind of handling is most appropriate in this case. And so you could roll back to a save point, or you could roll back to the entire transaction. But basically, Postgres can't do this for you. For fun, in the same circumstances, SQLite could do nothing, and then you would have to roll back by yourself, or it could roll back just the statement, or it could roll back the entire transaction, and you don't really have a way to tell what it's been doing. So the SQLite doc says, since you have no way to know, actually you should run a rollback by yourself anyway and roll back the entire transaction. And they're considering moving to PostgreSQL behavior in later release, but since they're very concerned with backwards compatibility, they haven't done it yet. So let's introduce a concept that's extremely common and that isn't even mentioned in the SQL standard. This is where it becomes interesting. Databases don't quite follow the standards that I've described, and the biggest difference is Autocommit. So what does it mean? Basically, Autocommit can be seen in a variety of ways that are pretty much equivalent. You could say that Autocommit is commit implicitly after each statement, which means that whenever you send a statement to the database will happen just commit afterward and see what happens. Or you could say that each statement lives in its own transaction. That's the same because since there's a commit after each statement, a new transaction is opened automatically before the next one, which we committed, etc. And well, for developers, usually they just treat it that, okay, just execute my query, I don't care. Run this query and save the results. And I think that's the reason why most databases default to Autocommit. At least SQLite, PostgreSQL, and MySQL do. Oracle is, well, it's complicated. I don't want to describe it. We can talk about it later on. So at this point, you may ask, since the database commits automatically, and we saw that the way to create a transaction was just to run a statement that would automatically create a transaction, when I'm under Autocommit, how the hell do I create a transaction? I can't anymore. And that's where start transaction becomes helpful, and that's probably why it was put in the standard. Actually, I don't know, but I suppose. When you're in Autocommit, if you run start transaction, it begins the transaction. During the transactions, your queries will not be committed. And at the end of the transaction, which is either a commit or a rollback statement, the database does a commit or the rollback and switches back to Autocommit mode. So what we're seeing here is that transactions and Autocommit are very tightly linked. Either you're using Autocommit or you're in a transaction. And actually, we'll see later on that for some databases, the way to create a transaction is just to turn off Autocommit. That's how it's actually implemented. So concretely, in PostgreSQL, the server always uses Autocommit as of version 7.4. I hope no one's running a version older than 7.4 because it's from decades ago or something. The documentation suggests that clients who want the standard behavior that is non-Autocommit implement it by inserted begin statements before statement when the transaction is not in progress. And typically the PSQL command does this. If you type a / set Autocommit off, it will start inserting begin statements, and so and then you have to commit a rollback by yourself, like I showed in the first slide. In SQLite, it's pretty much the same, except it's a bit more complicated. SQLite has a weird transaction model that's very tightly linked to the implementation as a file on disk. And whenever SQLite wants to read, it takes a shared lock, which also allows multiple processes to read from the same file. And when it wants to write, it takes an exclusive lock. And that determines the entire transaction semantics. And in particular, it means that transactions are always serializable on SQLite in terms of isolation level, because, well, you can serialize the order in which a transaction took the right lock, basically. So it automatically starts transaction except before select, because it doesn't need to do that because the shared lock guarantees that everything is going to do just fine. And it commits transaction almost as soon as you do them, except that if a read was in progress, it may have to wait until you finished reading all the rows from the cursor, and then it will come. Well, it's complicated, but basically it does autocommit the way you expect if you just use it from Python without doing any fancy stuff. we have finished the SQL and database layer, and we are now going to move on to the Python client libraries. The Python client libraries are typically SQLite 3, that's in the standard library, and PsychoPG2 for PostgreSQL. These are actually Python wrappers around C libraries provided by the database authors. For our purpose, the difference between the Python and C doesn't matter, so I will just call them Python client libraries, even if they're actually written in C or whatever. These libraries follow an API, the DB API 2.0, that's defined in PEP 249. And this PEP is very simple. It defines two kinds of objects, a connection that represents a connection to the database, and the connection is what you use to perform commits and rollbacks, so transactions are tied to connections. And it defines cursors, which is an object tied to a connection, and cursors is what you use to execute queries and to fetch results if your queries return results. It also defines exceptions and stuff, but these are really the main objects. PEP 249 says a few things about transactions. I actually extracted every sentence from the PEP that had the word transaction in the slide, I think. It says that if the database supports an autocommit feature, this feature must initially be off, which is kind of a bummer because we saw that for databases, autocommit is on by default. So the PEP follows the standard, but fights against the databases. So we have some kind of impedance mismatch here, and well, it triggers a lot of problems down the road. It also says that an interface method may be provided to turn it back on, and I love the fact that there's a back in this sentence, because it shows that the authors of the PEP were aware that the previous sentence forced them, would force the libraries to work against the database. That's kind of small telltale signs. And it also says that closing connection without committing will trigger a rollback, which is what you expect. If you don't commit, you will always have a rollback performed either by the library or the database. So let's check this with a quick example. I'm connecting to a PostgreSQL database with PsychoPG2. I'm executing a query that's inserting a row. I'm opening a new connection and trying to fetch the row, and very obviously, I don't get a result, because I forgot to commit. And if I add the commit, then I have the row. So here we have a conclusive proof that PsychoPG2 doesn't auto-commit by default. In detail, to implement this, PsychoPG2 has to track the transaction state. It has to know whether you're in a transaction or you're not. And if you're not, and you try to call cursor.execute something, it will run cursor.execute begin just before, and then it will run your query. So it starts a transaction for you. It does this for absolutely every statement, even select statement, because select statement in theory might have side effects. For instance, if you're calling a stored procedures or if you have triggers or whatever. You're calling a function, I don't know. You can disable this behavior by setting connection.autocommit equals true, and if you do that, PsychoPG2 stop inserting begins. In SQLite 3, it's pretty much the same story. It tracks the transaction state, but interestingly, it parses statements. So it parses the SQL you're sending. Since the grammar of SQL, as understood by SQLite, isn't too complicated, it's kind of doable. And if you're running a select, it doesn't do anything, which is consistent with SQLite not creating transaction for select statements. If you run a data modifying statement such as insert, update, delete, or replace, it will insert a begin before, so you will have to commit at some point. And before any other statement, insert a commit. And the rationale for inserting commits like this is that if you want to run a data definition statement, like an alter table or create table, you probably don't want to do that while you have uncommitted data, and so SQLite 3 will commit for you before running that statement. You can disable all of this by setting connection.isolation level equals none, which is a good candidate for the worst parameter name ever in the Python standard library, because this has absolutely no fucking relationship with the isolation level, and I'm going to swear if I continue speaking about this. It should be called something like transaction behavior because it can take more values, but the isolation level is always serializable in SQLite, and you can't do anything about that. Unfortunately, that's the least of the problems of this design. And the biggest problem is that any other statement triggers a commit, and if you run save point foo, SQLite3 will very helpfully commit just before your save point, which kind of negates the idea of making a save point in the first place. So as soon as you want to do something that has a relation with transaction in SQLite, pretty much your only choice is to go into autocommit mode so that it stops doing this. So there's a bug in the Python tracker about this, and it's considered a documentation issue. So, key learnings, besides my snarky comments about the SQLite3 module. The DB API requires the same transactional behavior as the SQL standard, and that's why you have transactions that are automatically started. Client libraries usually emulate this, and you can turn it off. The main drawback is that as soon as you run a statement, just a select, for instance, you have a transaction that's running, and so that's the root cause of the infamous idling transaction problem. If you just run a select query, you don't expect that you have to commit or roll back afterwards. But the DB API forces you to do that. And well, the PsychoPG2 docs are plastered with warning about this, and it still bites everyone, and it was a long-standing problem with Django. So I have some reservations about this design. Maybe we'll have a better DB API someday, but at the moment, that's what we work with. So in Django 1.5, there were a few problems. The default behavior of Django was exactly the behavior of the PEP, of the DB API 2.0. You run a select, it opened a transaction, and you could run more select queries in transaction just went on. And that's why the docs start by explaining that Django runs with an open transaction. Sentence, I don't find it very clear, but that's what it means. And at the end of the query, Django will eventually perform a rollback for you, so you don't leave a connection idle in transaction. Now, if we're adding a few writes on this schema, Django auto-commits after data modifying statements, which means if you run an update through the ORM or an insert or a delete, Django will automatically trigger a commit afterwards. So the complete list of functions that trigger this is save, delete, update, and bulk create. So this, the reason why it behaves like this, in my opinion, is that if Django doesn't do this and you just do query set blah blah something update, your update isn't saved, and so this dates back to before the 0.9 something ages. This is really very old code, and so I believe the commit was simply added so the changes would actually be saved. The doc says this is much like the auto-commit setting for most databases. As soon as you perform an action that needs to write to the database, Django produces the insert or update or delete statement and then does the commit. In my opinion, this is not quite like the auto-commit setting because you have this open transaction that runs from the time you run a read query until the time you run a write query. And when you see this schema, it's very hard to explain why it works this way, and that's why I believe it's mostly an artifact of history. You may have heard about the transaction middleware, which is a useful middleware that allows you to tie transaction to HTTP requests. What this middleware does is that it starts a transaction at the first time you do a request, and it will commit it only at the end of the HTTP request. So that looks a bit more sane. There's a small drawback, and that's why I'm saying that one HTTP request is almost equal to one transaction, is that it only works for the default database. There's a bug that dates back to the time MultiDB was merged, saying that the transaction middleware isn't aware of MultiDB. And there's a second drawback, which is that it may or may not apply to middleware, depending on whether your middleware run inside of the transaction middleware or outside. And in some cases, you can get in messy middleware ordering problem, especially if you have middleware that writes to the database. Yes, I forgot to mention something. What's interesting in the transaction middleware is that if your view function exits with an exception, and that triggers a 500 error, the middleware will roll back the changes. So whatever you've tried to do in your view function is forgotten, which is kind of useful. In addition to this, Django provides a few high-level APIs provided in Django 1.5, which are both context manager and decorators, and I've showed them here. So basically, transaction.commit.success is the same as the transaction middleware. When you exit the commit.success block, if you exit normally, Django will trigger a commit, and if you exit with an exception, Django will trigger a rollback. And inside the block, there's no commits. The ORM doesn't do the automatic commits. So that commit and success is kind of the standard way to do a transaction in Django 1.5. And then there's transactions that autocommit, which restores the default behavior. And well, it's mostly useful inside commit and success or inside the transaction middleware if for some reason you want to revert to autocommit. And there's commit manually, which I don't quite understand because it's just commit and success with a much more elaborate way to roll back if an error occurs, so it doesn't quite make sense. Below, there's a few low-level APIs that are very simple wrappers around the SQL statement. Well, the answer to how do they interact with the high-level management is badly. So how does all this fit together? I have to dive just for 1 minute into the guts of Django. Django used to maintain a stack of transaction management state to determine whether it was running in auto mode, which is the default mode of committing after each write, or in managed mode, where it doesn't do commits. That's the mode that's triggered by the transaction middleware and by commit and success. So anytime you enter one of these context managers, you add a mode to the stack, you add true or false, and when you pop from the stack, Django decides to do a commit or a rollback, and to decide this, it looks at whether there's an exception, and whether the dirty flag was set, that is, whether there was at least one write that should be committed. The reason is that if you didn't attempt to write, it's faster to roll back. The drawback is that you must remember to set it after you're doing raw SQL writes, otherwise your write gets rolled back. That's kind of a problem. Now, my biggest complaint with this design is that nesting doesn't work very well. So here's a quick example. I'm taking a query set of guitars. Inside the transaction.commit.success, I'm updating them. And inside, I'm entering a transaction.autocommit block. So we should go back to the normal mode. And I'm doing guitars.compute_rating, which is a function that does something and that crashes once in a while. Now, if you think that, well, compute rating is going to raise an exception. If you think that the update is actually saved, raise your hand if you think it is. Okay, no one thinks it is saved. If you think it isn't saved because the exception will trigger a rollback, raise your hand. Okay, and now everyone else raise your hand. You think it depends. Raise your hand. Okay, that's good, thank you. In fact, the answer is that it is saved because as soon as you enter the autocommit block, autocommit notices that you have an uncommitted write and triggers a commit. So it is always saved, in fact. And that's unsettling because that negates the effect of commit and success in the first place. Slightly more elaborate example is the same with commit manually. If you think, so this is exactly the same scenario, except I replaced autocommit by commit manually. If you think the brain change is saved, raise your hand. You can do it randomly, it will be fine. Okay, if you think it isn't saved, raise your hand. And if you think it depends, raise your hand. And you didn't dare raise your hand for it depends, and the answer is it depends in this case. So we'll skip the explanation, but my point here is just that as soon as you try nesting this context manager and you want to do that, it doesn't work. So if you don't understand anything of this, it's fine because it's going away, but that was mostly the justification of why it's going away and why you will have to change your code to upgrade to Django 1.6. Still, the transaction middleware is the only reasonable idea that I didn't shut down. And the decorator context manager, I've seen people try to do complex stuff with them, and it hurt a lot. So now I only have 1 or 2 minutes left to cover what's going on in Django 1.6. But fortunately, it's much more simple. In Django 1.6, the transaction management runs in database level autocommit mode. What this means is that Django is reverting the DB API, is setting the database connection to Autocommit, and so you get the most simple behavior you can imagine by default. Every statement run in its own transaction that's instantly committed. And that's probably what, as a Python programmer, you expect, unless you're familiar with the DB API. So if we add in a few write statements, it's the same. They're committed immediately. There's a replacement for the transaction middleware that is called atomic request. This is a parameter that you set in your settings on a per database basis, so that solves the problem with multiple databases, and it only covers the view function, which solves the problem of whether middleware is or is not included. I believe that middleware isn't intended to crash in any way, or middleware should do its own error handling. So in your middleware, and especially in response middleware, you can assume that the database connection is usable, because if there were an error, atomic request took care of doing the rollback when exiting the view function. So that's kind of cool. This is the most important slide. So I'll spend my last 30 seconds on this. There's one high-level API that's a lot like commit on success. It's the API to do transactions. It's called atomic to stress the fact that the defining property of transaction is atomicity, like I said earlier. It works mostly like commit on success. It triggers a rollback on exceptions, but its main advantages is it can be nested without any restriction, and it's using save points for that. So if you're already in atomic block and you enter a new block, Django will put a save point, and so if you have an exception in the inner block, it will roll back to the save point, and the outer transaction is still live and can still be used. So this concept is totally stolen from something Christoph wrote that's called the exact. And the second property is that it guarantees atomicity. So for example, if you try to do transaction that commit inside an atomic block, Django will not let you do that. It will read as an exception. That's particularly helpful if you're calling some third-party library that may be doing something. It guarantees that it won't mess your transaction handling. And so I'm going to skip this and this. You still have the same low-level APIs as before. I didn't touch them. The only reason why you would want to use them if you want to implement your own transaction management, but I firmly believe that there's only one way to use them all together sanely, and that's atomic. So I hope you will like transaction management in Django 1.6. If you didn't understand what I say, go to the docs and learn it, and use atomic whenever you need atomicity. Thank you.